Space is not tidy, it is noisy, uneven, and shaped by chance. Objects tumble, fracture, vent, and erode in ways that rarely repeat themselves. When symmetry appears at large scales, scientists take notice because nature almost never insists on precision without a reason. Now consider this. An object from another star system enters our solar neighborhood, not bound to the sun, not born here, and instead of behaving like a chaotic interstellar relic, it displays order, repetition, balance. This object is known as 3I Atlas. At first glance, it looks ordinary, a faint point of light wrapped in dust and gas, drifting silently through the dark. But when astronomers stripped away that haze, something unsettling emerged. 3 narrow jets of material, evenly spaced, erupting from its surface, each separated by roughly the same angle. Not random, not messy, precise. Why does that matter? Because on objects like comets, jets usually form wherever ice happens to crack or sunlight happens to strike. They appear, fade, shift, and disappear. They are accidents of heat and structure, but these jets stayed fixed, balanced, stable. Space produces chaos by default, so when something resists chaos, it raises a quiet alarm. This is not a story about aliens, not yet. It is a story about discomfort, about data that refuses to sit neatly inside familiar categories, about an object that seems too organized for comfort, yet too subtle to dismiss. Over the next few minutes, we will follow the path of 3I Atlas from its discovery to the data that divided astronomers, to the theories that struggle to explain it, and finally to a moment still ahead of us when this visitor will face the strongest gravitational test of its journey. Whatever 3I Atlas truly is, it is asking a question, and we are only beginning to understand what that question might be. The discovery of 3I Atlas did not begin with excitement. It began with routine. Every night, automated sky surveys scan the heavens, comparing images taken minutes or hours apart. Their task is simple in principle: find anything that moves. Most of what they detect turns out to be familiar. Asteroids looping around the sun, known comets returning on predictable paths, space debris closer to home. In July 2025, one object stood out. It was faint, fast, and moving on a trajectory that immediately raised eyebrows. Its path did not curve the way solar system objects usually do. Instead, it followed a hyperbolic trajectory, a telltale sign that it was not gravitationally bound to the sun. This was not a visitor from the Kuiper belt or the Oort cloud. It was passing through, never to return. Follow-up observations began almost immediately. Ground-based observatories tracked its motion night after night, refining its speed and direction. Radio facilities like the Green Bank Telescope and communication networks such as the Deep Space Network helped constrain its velocity and position with extreme precision. The numbers were unambiguous. 3I Atlas was moving too fast to belong here. That alone made it historic. It became only the third confirmed interstellar object ever detected in our solar system, following 1I Oumuamua and 2I Borisov. Each of those earlier visitors had challenged expectations in different ways. Naturally, astronomers wondered whether this one would do the same. At first, there was little cause for concern. Early observations suggested a comet-like object surrounded by a coma of dust and gas. That was reassuring. Borisov had behaved like a textbook comet, just one that happened to come from another star. Expectations were modest. Measure its brightness, estimate its size, track its rotation if possible, document its composition. Another data point in an emerging category of interstellar debris. But discovery is only the beginning of understanding. As weeks passed and data accumulated, subtle inconsistencies began to emerge. The object's activity did not fluctuate as expected. Its motion showed hints of non-gravitational forces. Nothing dramatic, nothing headline-worthy, just enough to make scientists look twice. History has shown that the most disruptive discoveries often arrive quietly, not with explosions, but with numbers that refuse to behave. By the end of the initial observation phase, one thing was clear: 3I Atlas was not going to be boring. To understand what made 3I Atlas unusual, astronomers had to look past what the eye could see. A comet's coma is deceptive. It is bright, expansive, and chaotic, a cloud of gas and dust produced as sunlight heats frozen material. Beneath that glow lies the nucleus, the true body of the object, usually hidden from direct view. Extracting structure from this chaos requires specialized techniques. Astronomers apply digital filters that suppress static dust and enhance features that rotate or evolve with the object itself. These methods allow scientists to separate genuine physical structures from visual noise. When these techniques were applied to high-resolution images of 3I Atlas, the results were unexpected. 3 narrow jets of material emerged from the coma. They were thin, persistent, and sharply defined. More striking than their appearance was their placement. Each jet was separated from the others by roughly the same angle, forming a near-perfect triangular pattern around the nucleus. Jets on comets are common, but they are rarely symmetrical. They turn on and off. They wander as the object rotates. They vary in strength depending on surface composition and sunlight exposure. Randomness is the rule. Here, randomness was absent. The jets remained stable over time. Their brightness fluctuated together. Their spacing did not drift. This implied a level of rotational balance that is difficult to maintain on a loosely bound body of ice and dust. Spectral analysis deepened the mystery. The emissions did not perfectly match those of typical cometary volatiles. Some expected signatures were weaker than anticipated. Others appeared in ratios that suggested unusual surface or subsurface structure. Even more puzzling was the object's motion. Like Oumuamua before it, 3I Atlas exhibited subtle non-gravitational acceleration. This means its trajectory could not be explained solely by gravity. For comets, this usually results from asymmetric outgassing, jets acting like tiny thrusters. But if jets were causing the acceleration, they were doing so with remarkable balance, enough force to alter the path, yet arranged in a way that minimized wobble and tumbling. This is where discomfort set in. The data was internally consistent. Independent instruments agreed. The measurements held up under scrutiny. There was no obvious error to blame. Scientists were left with a paradox. An object behaving like a comet, but not quite like any comet we know. Emitting material, but doing so with an efficiency and symmetry that felt engineered rather than accidental. No conclusion could be drawn yet. Science does not work that way. But the data forced a pause. When observations resist easy classification, the correct response is not speculation, but patience. Still, one question lingered beneath every analysis. Was this simply an unfamiliar product of another star system, or were we missing something more fundamental? When data refuses to cooperate, theory expands. The first explanations proposed for 3I Atlas were conservative. The object could be a comet formed under different conditions than those in our solar system. Other stars have different radiation environments, disk chemistry, and formation timelines. Perhaps this object simply reflected that diversity. One popular model suggested a contact binary. In this scenario, two or more small bodies gently collided long ago and stuck together, creating a lumpy, irregular shape. Such objects are common in our solar system. If vents happen to form at balanced locations on such a structure, symmetry might emerge by chance. Another idea proposed layered composition. If the nucleus contained repeating bands of volatile material, heating could activate jets in a coordinated pattern. Rotation might then reinforce that alignment over time. These explanations were plausible. None violated known physics, but each came with problems. Maintaining precise symmetry on a rotating, eroding body is difficult. Stress fractures propagate unpredictably. Material strength varies. Solar heating is uneven. Over time, small imbalances grow. Yet 3I Atlas appeared to resist this tendency. Statistical analysis added pressure. The odds of three independent vents aligning so precisely, activating simultaneously, and remaining stable were low. Not impossible, but uncomfortable. This opened the door to a more controversial question. Could the observed symmetry be a technological signature? The idea was not new. Scientists studying technosignatures look for patterns unlikely to arise naturally, perfect repetition, optimized geometry, efficiency where inefficiency is expected. These are not proofs but clues. Some researchers cautiously noted that the jet arrangement resembled stabilization systems used in spacecraft and satellites. Balanced thrust minimizes rotation. Triangular configurations maximize control with minimal force. Importantly, no one claimed this was a spacecraft. The artificial hypothesis was framed as a question, not an answer. If this were technology, it would represent something far beyond our own capabilities, operating passively, without communication. Skeptics pushed back hard, and rightly so. Nature often surprises us. Snowflakes form perfect hexagons. Crystals grow with astonishing regularity. Biological systems produce symmetry through evolution, but scale matters. Symmetry becomes rarer as systems grow larger and more chaotic. In the end, neither theory won. The natural models struggled with probability. The artificial models struggled with evidence, and that is where science is most honest. At the edge of knowledge, certainty is rare. 3I Atlas remains a puzzle, not because it proves anything extraordinary, but because it refuses to fit comfortably anywhere at all. The story of 3I Atlas is not finished. In March 2026, the object will pass near Jupiter, the most massive planet in the solar system. This encounter is critical, not because Jupiter will reveal secrets intentionally, but because gravity is unforgiving. Jupiter's tidal forces have a history of destruction. Comets that stray too close are stretched, fractured, and sometimes torn apart entirely. Shoemaker-Levy 9 is the most famous example, shredded into fragments before colliding with the planet. For 3I Atlas, the flyby represents a stress test. If the object is loosely bound, composed of fragile ice and dust, Jupiter may disrupt it. Jets could destabilize, rotation could change, the nucleus might fragment. If the object is cohesive, its structure may hold. Jets may continue firing in the same pattern. Acceleration may remain controlled. Scientists will watch carefully for deviations. Any unexpected change in trajectory beyond gravitational predictions would be significant. Non-gravitational acceleration near such a massive body would be difficult to explain. Observatories across the electromagnetic spectrum will be involved. This may be the closest, clearest look humanity ever gets at this interstellar visitor before it departs forever. The flyby will not answer every question, but it will eliminate possibilities. And in science, eliminating possibilities is how truth slowly emerges. March 2026 is not a conclusion, it is a filter. 3I Atlas is not remarkable because it came from another star system. We now know that interstellar visitors are likely common. What makes this object unsettling is its restraint, its balance, its refusal to behave messily. From discovery to data, from theory to anticipation, the story has remained the same. Precision where chaos is expected, stability where erosion should dominate. Natural explanations struggle, but remain possible. Artificial explanations intrigue, but remain unproven. Between them lies uncertainty, the most honest state of science. Perhaps 3I Atlas is a rare natural configuration, a statistical outlier drifting briefly through our awareness, or perhaps it represents something we do not yet have the framework to recognize. Either way, it has done something important. It has reminded us how limited our understanding still is. The universe does not owe us clarity. It offers hints, patterns, and anomalies, and it is our responsibility to approach them with curiosity rather than fear. As 3I Atlas approaches Jupiter, we wait, not for confirmation of belief, but for information. Whatever the outcome, it will expand our knowledge of how objects form, travel, and survive between stars, and if this is only the beginning. If more visitors like this follow, then the silence of space may not be as empty as we once thought. The question is no longer whether we are alone, it is whether we are ready to recognize what passes quietly through the dark.